for 2020. Okay, so we are going to check back in with some work that you did yesterday with Mr. Murphy. This is a chi-square scenario, and it is a multiple choice question from an old AP exam. So let's just jump right in here. It says, the following two-way table resulted from classifying each individual in a random sample of residents of a small city. Now I'm going to pause right there, and I'm going to say that the random sample of residents of a small city, that sounds to me like one sample that they're taking from one population. So I'm just going to note right here that this is one population. And then let me keep reading here. According to level of education, with categories earned at least a high school diploma and did not earn a high school diploma, and employment status, with categories employed full-time and not employed full-time. Now, what it sounds like to me there is we have two different variables, level of education as well as employment status, both of which are categorical variables. So I'm definitely seeing two categorical variables here. And so anytime we have one sample or one population with two variables, that is a clue to us that we want to be doing a chi-squared test of association, also known as a chi-squared test of independence. So let's continue reading. The other clue, by the way, is the fact that we have a two-way table here. The two-way table is sort of a giveaway to you that you're either going to be doing chi-squared test of homogeneity or chi-squared test of independence. So here's what the question says. If the null hypothesis of no association between level of education and employment status is true, which of the following expressions gives the expected number who earned at least a high school diploma and who are employed full-time? So we see that word association in there again. That's another clue to us. And this sounds like we're going to have to be doing an expected value calculation, assuming the null hypothesis is true, that there's no association between these two variables. Now, they said for at least a high school diploma. So I know that I'm dealing with the first row here, and employed full-time, that is the first column. So what we're really looking for is the expected value in the top left cell of this two-way table. Now, if the null hypothesis is true, we should be able to just look at the proportion of the total sample that earned at least a high school diploma. And I can do that by taking the row total there divided by the grand total, 92 out of 157. That's going to tell me the proportion of the sample that earned at least a high school diploma. Now, if the null hypothesis is true and there's no association, we would expect that proportion to hold for this group of people as well as this group of people. In other words, the proportion would be the same within each one of those columns. Now we know we want to deal with the first column here. And so this is the proportion, and we know the total within that column is 82. So we should be able to take the proportion of the total there to get our answer. And sure enough, if you look at the answer choices, that does in fact match with answer choice B. And I just want to make note that this does in fact match with the formula that we talked about over the last couple of lessons here, which is how to calculate an expected count when you have a two-way table by taking the row total multiplied by the column total, all divided by what I like to call the grand total or the table total. And sure enough, you can see here, it is the row total multiplied by the column total, all divided by the grand total there. So our final answer on this one is going to be B. Hope you did all right on that one. Okay, we are now ready to shift gears. So we're going to move into the lesson for today. And I like to start always with a couple of learning targets, just so that you know where we're headed. This is also a way where we can measure at the end of the lesson whether or not we actually got what we needed to by checking back in with these learning targets here. So there are three of them. Okay, the first one is to identify and interpret parameters and statistics, which hopefully are familiar terms with you, from linear regression. So we are going to be doing some review of stuff that you likely covered very early in the class with two variable analysis, scatter plots, residual plots, all of that stuff. We'll be doing some review with that, but then moving into this new realm of inference for linear regression. So the second learning target, in order to do inference, we're going to have to think about the sampling distribution of the sample slope. And then finally, the third one is to check conditions for inference for slope. And that's really just going to be setting us up for the next two lessons where you're going to calculate a confidence interval and a significance test for a slope. And there are some conditions that must be met in order to perform that inference. So we'll check back in on these learning targets when we get to the end of today's lesson. So let's move right into today's lesson. And the context for today's lesson has to do with SAT scores and GPA. And my hunch is that if you knew something about a student's GPA, that it might help you to predict what their SAT score might look like. Not perfectly, but it might help us to predict a student's SAT score. So here's what it says. It says, how well can we predict SAT scores from students' grade point average, GPA? Let's start by looking at data from all 330 seniors at a high school in Michigan. Now, what we're given here is some computer output, which is going to be very, very important for us. And you likely saw this earlier in your course, but there are some numbers that are in that computer output that you had no clue what they meant. But listen, by the end of the next couple of lessons, you are going to know what those numbers in that computer output represent. And then, of course, we have a scatter plot. And sure enough, as I had sort of predicted, you do see that there is a very clear positive linear relationship here. I'd say a fairly strong positive linear relationship, such that the higher the GPAs, their students are more likely to have higher SAT scores. So above average GPAs tend to be paired with above average SAT scores. And of course, we can find a line of best fit for that, and we can do some analysis. So let's jump right into the questions for today. So number one is just to start thinking about what the population is in this particular context. And it's given to you right up front, and in fact, I've underlined it already. It is all 330 seniors at a high school in Michigan. So this is something that is very rare in statistics. It's we actually have data on every single person in the population, right? So later in the next part of the activity, we'll think about what happens if you only have a sample of the whole population. But for now, we do in fact have all of the data from the entire population here, all 330 seniors at this high school in Michigan. Okay, the next question says, what is the y-intercept of the LSRL? And of course, LSRL stands for the least squares regression line, which we're given some information about in our computer output here. And so hopefully you know what a couple of the numbers in this computer output mean. The first one that we need is the y-intercept. And that is in fact that first number in the top left that you're given there. So we can record that the y-intercept is 611.4. Now, the next value that we're given in that computer output is the slope of the LSRL. That's the next value that you see there. So we can record that for the next question. The slope of the LSRL is 198.1. And in just a minute, we'll talk a little bit more about what that number means specifically and how to interpret that slope. But the next question says, what's the equation of the LSRL? Well, we know the y-intercept and we know the slope. So we can write our equation now as y equals the y-intercept plus the slope times x. Now, there's a couple of things that I want to change real quickly about that line of best fit that we just wrote down there. First of all, I try to get my students in the habit of using contextual variables. And what I mean by that is instead of using x and y in your equation, why don't we write down what those variables actually represent here? And so instead of writing x, we know that x in this particular context represents the GPA. So I'm just going to put GPA as the x variable. And we should do the same thing for the y variable here. The y variable for this particular context is we're trying to predict the SAT scores. And then the last thing that I think is super important here, so tiny little symbol, putting a little hat over the SAT. And what that means is predicted SAT. Because remember, the whole point of this least squares regression line is so that we can choose an X value or a GPA, and then hopefully make some sort of prediction about what the SAT score would look like for that particular GPA. So let me just point out a couple of things here. The y-intercept and the slope that we just got from the computer output there. I want to make note of the fact that these are values that come from data from the entire population, okay, which is rare for us to have all of the data values from the whole population. So because these are numbers that are calculated from the whole population, these are what are known as parameters. And usually when we're talking about parameters, we have some very specific notation symbols that we use for them. So I'm going to tell you the right symbols here. For the y-intercept of this LSRL, we're going to call that alpha. And let's be careful here. This is not the same as the alpha significance level from a significance test. This is totally different, a different alpha. And then for the slope, we're going to just go in order of our Greek letters here. This is beta. So we have alpha for the y-intercept and beta for the slope of the population least squares regression line. And then I want to really point out the fact that this least squares regression line that you see right there comes from data from the entire population. So this is what's known as the true population LSRL, right? That is the true line of best fit for the entire population. And let me just remind you of this notation that we used here. Equals, we said alpha plus beta x. Now, I think we're used to writing y here. And it turns out, and I'll show you how this works in just a second here, that what we should actually be writing here is the mean of y. And after we talk through question number 3, I think that'll make a little bit more sense here. But at least you know the correct notation for the true population LSRL. Okay, we are ready for question number 3. So question number 3 says, predict the SAT score for a student with a 2.0 GPA, a student with a 3.0 GPA, and a student with a 4.0 GPA. So let's start out with our student that has a 2.0 GPA. Now we know that's our X value, right? And we know that we can take the line of best fit and predict the SAT score by plugging in that particular X value. So our predicted SAT score here, just using our line of best fit, 611.4 plus 198.1 times the GPA, but in this case, the GPA is 2.0. And I will tell you that the predicted SAT score for a 2.0 GPA is about 1,008. That's the predicted SAT score for a student with a 2.0 GPA. But I want to be a little bit careful about this. If you look back at the scatter plot on the top of the page there, and you find our X value right here, right? This is an X value of 2.0 GPA. If I go up to the data, what you're going to realize here is that there's not just one student that has a 2.0 GPA. In a large school like this, you're going to have quite a few students that have a GPA of 2.0. And each one of them might have a slightly different SAT score. We see some variability in the SAT scores for that particular GPA. And so just to give you a visual perspective of this here, if we're looking at students that have a 2.0 GPA, we got 1,008 as our prediction for what their SAT score is. Now, most of them will probably score fairly close to 1,008, but there might be a few that are a little bit above, and there might be a few that are a little bit below. And what you're going to find is that that appears to follow somewhat of a normal distribution. In other words, for a specific X value of 2.0, the distribution of the Y values or the SAT scores is approximately normal. So I'm going to go ahead and draw a normal distribution right on top of that. And I'm going to try and draw a 3D picture here for you. I'll do my best. What we're really saying here is that when we go back to this X value of 2.0, there's really a normal distribution. And we know that the center of that normal distribution should be about 1,008. So it's really like three-dimensional almost. We have like a normal distribution right there at the X value of 2.0. And the center or the mean of the normal distribution is 1,008. This is precisely why we're using this notation here, right? So we're actually not just predicting the SAT score for a single student with a 2.0 GPA. We are predicting the mean SAT score for all students that have a 2.0 GPA, which we would expect to be at the center of this normal distribution that we have here. Now, we're going to use some similar reasoning for the next student, which is the student that has a 3.0 GPA. And we can start by plugging in that particular X value into the line of best fit. And I've done that calculation already. And it turns out that a student with a 3.0 GPA is going to have a predicted SAT score of about 1206. So if I go back to my scatter plot here and I now look at students with 3.0 GPAs, you're going to find that there are quite a few students that have GPAs of 3.0, and that the mean value of all of those scores is going to be about 1206, what we predicted from the line of best fit. And so let's get a visual representation of that again. 1206 we would expect to be at the center of the distribution. Most students score fairly close to 1206, but some of them score above and some of them score below, such that the distribution of SAT scores is approximately normal, which means in my picture up here, I can draw in a normal distribution where the mean is about 1206. Now you can see where I'm going here. Let's move over to the final estimate, which is the one for the GPA of 4.0. And I'll tell you, just by plugging that into the line of best fit, you're going to get a prediction of about 1404 for a student with a 4.0 GPA. If we come back up to our scatter plot here and we look at the students that scored a 4.0, we're going to see that the average is going to be about 1404 for all of those students. 1404. Got another normal distribution here, where the center of the distribution is at about 1404. So just to finish off my picture here, 1404, most values close to it, a little bit less as we get further away, and we've got this normal distribution here. And so what we actually have in the scatter plot is we have like a whole bunch of these normal distributions. In fact, for every X value or for every GPA, we have a normal distribution of SAT scores. And listen, if we were to draw a line through the center of each one of those normal distributions, right? So I'm going to go ahead and try and draw a line through the center of each one of these normal distributions here. This is going to be our line of best fit, right? That's actually the population LSRL, the true population LSRL is what I've just drawn in there for you. And it goes right through the center of every one of those normal distributions. Now, one other thing I want to point out before we move away from these normal distributions here is the variability of each one of these normal distributions. And one of the ways we could measure that, of course, is with the standard deviation, right? So the standard deviation I can represent in the picture like this with a symbol sigma. And I could do the same thing in the next picture here. This would represent the standard deviation, and this would represent the standard deviation. And it turns out that one of the conditions that we're going to need to check is that each one of these normal distributions has about the same variability or equal standard deviations. In other words, that sigma value stays the same for each one of these normal distributions here. And so this value sigma, you can actually get from your computer output up here. It's labeled as S here, but that's because the computer thinks that this is a sample. It turns out that this is in fact sigma, well, very close to sigma. The calculation is slightly off, but that's a very, very good estimate of what the standard deviation of the Y values is for each one of the specific X values. Okay, so we've taken care of that whole normal distribution thing. I've done my best to draw you a three-dimensional picture in the best way that I can. And we have arrived at the final question for this page, and that's to interpret the slope in the context of the problem. And that's going to become a very big deal over the next two lessons where we're doing all of our work with slope. And so the slope here, beta, is, we've already calculated it, is 198.1. And just as a real quick reminder of slope, here's a hint that you can use to interpret your slope. When you first learned slope in your very first algebra class, You may have learned it as the rise over the run, or even possibly as the change in y over the change in x. And if you put that in the context of the problem, change in y would be the change in the predicted SAT score divided by the change in the GPA. And we know that value is 198.1. And I'm going to write it as a fraction over 1. And so really, it's telling you that for a change in GPA of 1, we would predict the SAT score to have a change of 198.1. So we just need to go ahead and put that into words now. Okay, so here's the interpretation. It's going to say, for every increase of 1 in the x value, which is GPA in this case, for every increase of 1 in GPA, we predict an increase in SAT score of 198.1 points. Right, we've essentially just taken this here and turned it into words. Now, a couple of things you want to make sure that you include in your interpretation of the slope. You're always going to talk about an increase of 1 in whatever the x variable is. For us, that's GPA. Very important here is that you use the word predicted for the y variable, which is SAT. So it is a predicted SAT score. And then notice here that I've said that it's an increase in SAT score. And I know that because the slope is a positive slope, right? If it was a negative slope, I would expect it to decrease. And then, of course, here is our slope value. And we've also included some units on this one here. So very important moving forward, this idea of slope, right? The slope of the least squares regression line. The next two lessons very specifically are going to be inference about this value for slope. But here's the thing. In order to do inference, we have to have a sample from which we can make an inference to the population. And everything that we did here on this first page, remember, was population data. We had all 330 seniors. So the next move that we're going to make, if you flip to the next page, we are now going to move into the world where we take a sample from the population, which is much more likely in the real world that we have a sample rather than all of the data from the whole population. So let's see how things change here when we now are taking a sample from the population. So it says, let's now consider the situation where we take a random sample of 10 seniors from this high school in Michigan. And just like we had on the previous page, we've got our computer output here, and we've got a scatter plot of the data. But you'll notice a lot less dots in our scatter plot or data points because we only have a sample of 10 seniors. So question number one, to define the population. Well, I think we did that already on the previous page. That's all 330 of the seniors at this high school. But this time we don't have data for all of these students. We only have a sample. And so the sample in this case is the 10 seniors that have been randomly selected. Okay, so the format of this page is going to look very similar to the previous page, so I think we can move pretty quickly through this. For the y-intercept and for the slope, we know exactly where we're going to get those. The y-intercept is the first value here. The slope is the second value here. So let's go ahead and record our y-intercept as 724.4. And let's record our slope as 169.0. And now we know our equation of the least squares regression line. It's going to say that the predicted SAT score equals 724.4 plus 169.0 times the GPA. Now, the thing that's different here is we are dealing with sample data. And so this value that we have for the y-intercept and for the slope is now a value calculated from a sample rather than a value calculated from the whole population. And for that reason, these are considered statistics, right? Remember, statistics are calculated from samples. Parameters are calculated from population. And once again, the notation or the symbols that we use is going to matter here. And this is the part that's going to look familiar to you from previously in the course. The y-intercept, we're going to call a, lowercase a, and the slope, we're going to call b. That should look very familiar to you, okay? And let's just point out here that this line that we just created the equation of, that is not the population LSRL, that is the sample LSRL. And we use different notation for the sample LSRL. And this is the part that I hope looks familiar to you. Y hat equals a plus bx, which is something that you likely studied earlier in the course. Okay, so let's move on to number 3, which says, what is the sample slope? Is it the same as the population slope? Well, we know from above here that the slope of the sample, that's B, which we know is 169.0. And the population slope, that is the beta value from the previous page. And if you look back, the true slope of the population LSRL was beta equals 198.1. So is this a good estimate? Yeah, it's a fair estimate. It's definitely not the same though. So I'm going to say right here very clearly that our sample slope is not exactly equal to the population slope. And the question is why? Okay, and the reason is when you take a random sample of 10 students, every time you take a random sample of 10 students, you're going to get a different sample of 10 students. And then sure enough, this line of best fit is going to be a different line of best fit. And every time you calculate a different line of best fit, you're going to have a different slope value, right? So at the heart of this is the idea that we are taking a random sample, and we know that random samples produce sampling variability. So we're going to say because random samples create sampling variability. So every time you take a sample of 10, you're going to get a slightly different slope value. Well, that leads us right into question number 4 here, which says, suppose we selected many, many random samples of 10 students and each time found the sample slope of the LSRL. Predict what the distribution of these sample slopes would look like. Okay, so I'm a big fan of the dot plot. So we're going to draw ourselves a dot plot here. And, you know, we got a slope of 169.0, and you'd put that dot down. But then the idea is if we took another sample, random sample of 10 students, we'd get a slightly different value, and maybe it'd be a little more, maybe it'd be a little less. And you may well predict here that if you were to do this over and over again, you're going to get a pretty nice distribution of values here that might look something like this, right? And I'm hoping right now that you're saying, oh, that looks like a normal distribution. And we could draw a normal curve on top of that. Now, let's make sure that we understand what this distribution represents. If I were to pick a single dot there, okay, what that dot represents is one random sample of 10 students. Then we calculate the line of best fit for those 10 students, and then we grab the sample slope from that line of best fit, and we plot that value right here. So that is one random sample and the slope calculated from that random sample. And this is a different random sample of 10 and the slope calculated from that sample. And this is a different sample, and this is a different sample, and this is a different sample. And so what we have here is what we call the sampling distribution of B, the sample slopes, because each one of those dots represents a different value for the sample slope based on a different sample of 10 students. Now I'm going to hope that that comes out as approximately normal. I can label that as capital N. And now let's think about the center and the variability of this distribution. Now the center of this distribution, I would hope, would be close to the truth. And in this particular context, we actually know the true slope of the population LSRL. It's 198.1. And so hopefully these random samples we're taking are going to be pretty close to that thing that we're trying to estimate here. Now, sometimes a little higher, sometimes a little bit lower. But in general, the mean of this sampling distribution should be the true slope of the population LSRL. Now, for the standard deviation of this thing, we're going to call this the standard error of B. And it turns out there's a big formula for that you can use to calculate it. But most of the time, we're going to get that value right from the computer output here. So you see up above where it says standard error of the coefficient. And we know that this right here is our B value. It turns out that this value right next to it is the standard error of B, right? That's the value we're looking for. That's 32.0. And what that's telling you is that these estimates for the slope that we're making will typically be about 32 away from the truth, right? That's what that standard error is telling me. Now, one other thing I'm going to point out just while we're here is this S value is what's known as the standard deviation of the residuals. And that's actually an estimate of that sigma value that I showed you on the previous page. Okay, so S estimates sigma, which is the true standard deviation of the Y values for each X value, right? This is our best guess at it, is S, the standard deviation of the residuals. Okay, let's move on back down here. Number 5, what is this graph? Now, I'm hoping this one looks familiar to you and that you studied this earlier in the course. This is what's known as a residual plot. And just as a very quick reminder of what a residual is, if you look at your scatter plot, the residual is the difference between the actual Y value and the predicted Y value. So this student right here, if we were to calculate the difference between the actual Y value and the predicted Y value here, that difference would be the residual. So this would have a fairly large positive residual for this particular student. And you'll see that student represented in the residual plot right here, okay? And also notice that you've got 0 at the center of all the residuals, and you got some positive, some negative. And then on the x-axis, we're actually just graphing the x values, the GPA. Now move on over to the next graph, and you'll notice that it's a residual. And so students will say, oh, it's a residual plot. Well, not exactly, right? The residual plot has residuals on the y-axis and x values on the x-axis. This is a little bit simpler than that. It's simply a dot plot of all the residual values, right? There's only one variable there, the variable of residuals, and we're looking at the distribution of those residuals. Okay, we're going to need those when we get down here to checking conditions for inference. And don't freak out. There are 5 conditions for inference. I know we're used to 3 conditions generally when we're doing inference for means or proportions, but a couple of these are going to look very familiar to you. So let me tell you first what they are, and then we'll start with the ones that we already know how to take care of. So there is this acronym LINER, which will help you to remember the 5 conditions, which are linear, independent, normal, equal standard deviation, and random. And I'm going to start with the ones that are easy, the ones that we already know. First of all, the random condition, we've been using this one all year long. We just got to make sure that we have a random sample. And sure enough, we see from the question that this is a random sample of 10 seniors. And of course, this is important because we want to be able to generalize to the population of all seniors. And we also want to know that each individual senior is independent of the next, which is ensured by the fact that this is a random sample. Now, the next one that we already know how to do is the independent condition, also known as the 10% condition, which is an issue if you are sampling without replacement. And in this particular case, we are sampling these 10 seniors without replacement. So we do have to check the 10% condition. So the 10% condition here would say that the sample is less than 10% the population, which is all seniors at this school. And actually, we know that there are 330. So I would definitely say that the independent condition is satisfied. Now to the 3 new conditions here. The first of which is that there is a linear relationship between X and Y. And well, we know that because we can look at the scatter plot and see that the scatter plot seems to be fairly linear there. So our justification for why this condition is met is to say that the scatter plot is fairly linear. Now, the other thing that we can use, actually, if we look right above us here at the residual plot, if you recall from earlier in the year, we're looking for a residual plot that has just sort of a general scatter above and below the x-axis. What you don't want to see there is like a curved U pattern or an upside down U, which we don't see here. So I'm going to add that in. I'm going to say also the residual plot shows no clear pattern. So for both of those reasons, I'm going to say that for sure the linear condition is satisfied here. Okay, now for the normal condition, this goes back to what we were talking about on the previous page with these normal distributions here and with this scatter plot that has all these normal distributions. What we're trying to say is for each x value, the distribution of the y values is approximately normal. And the way that we're going to check that here is we're going to look at this dot plot of residuals. Okay, and hopefully we see something that looks relatively normal there with the dot plot of the residuals. But surely we don't want it to have an outlier or strong skew. So I'm going to say here that the dot plot of residuals shows no strong skew or outliers. And of course, we could have used the histogram or a box plot. I just happen to prefer the dot plot myself personally. All right, now equal standard deviation. What we're talking about on that one is the fact that these three normal distributions all have similar or the same standard deviation sigma there. We want to know that that's true, that there's equal standard deviation. And the way that we're going to check that is we're going to look back up here at this residual plot, and we'd like to see that the residuals have just about equal variability for each x value. So as I go through all the x values here, I'd like the variability of the y values to be mostly the same. So I'm going to say here that the residual plot shows the variability of y is similar for each x value. Now, what we wouldn't want to see there is like a residual plot that looked something like this, where the residuals started out very close to the x-axis and then got much, much bigger there, right? That would be a problem because the variability is increasing as you move to different x values. So this would be bad news. But I think we're okay in this particular situation, which means all 5 of our conditions are satisfied. We'd be ready to perform inference. Okay, so let's see if we can summarize what we learned here in today's activity. I'm going to go back to the 3 learning targets that we had at the beginning, starting with number 1, which had to do with identifying parameters and statistics. And so I think the important takeaway here is about notation, right? For the population LSRL, we say the mean of y is equal to alpha plus beta x, whereas the sample LSRL, we use different notation here, and this is the one we're more familiar with, y hat equals a plus bx. And so what this means is that that a value, which is the sample y-intercept, is going to be used to estimate the alpha, which is the true y-intercept for the whole population. B is going to be used to estimate the slope of the population LSRL beta. And then I'm going to add one more in here, which we mentioned on the previous page, that S, the standard deviation of the residuals, is going to be used to estimate sigma, which is the standard deviation of y for each x value. So very important here, all these values that we have here, because they're based on a sample, those are statistics. All these values, because they're based on the population, are parameters. Okay, that moves us to learning target number 2, which had to do with the sampling distribution of the sample slopes. And I think for this one, I'm just going to draw a picture of the sampling distribution of B. And really it's a dot plot, right? So there's a bunch of dots in here, but I'm modeling it with the normal distribution. And we said that the true value, or the center, the mean, should be the true slope of the population LSRL, beta. And we can measure the standard deviation using SEB, the standard error of the slope. And that generally is going to come from computer output. And we're going to need that in the next 2 lessons when we do inference for regression. All right, finally, is to get to these conditions, all 5 of these conditions that we have for learning target number 3. Remember the acronym is LINER. That's going to help you to remember the 5 conditions that are necessary here, which is linear, independent, normal, equal standard deviation, and random. And just as a quick reminder for each one of these on how you're going to check that, the linear condition you can check by making sure that the scatter plot is fairly linear, or that the residual plot has no clear leftover pattern. Independent condition is 10%. We check that when we're sampling without replacement. For the normal distribution, you're going to check the dot plot of the residuals, or a histogram, or a box plot. Equal standard deviation, you're going to check your residual plot. And what you don't want to see is those residuals getting bigger as you move to the right or smaller as you move to the right. And then random, we know this one, we just need a random sample. All right, now your homework problem is listed there. That is the problem that Mr. Murphy is going to start with in the next lesson. What I tried to do here today is I tried to set the stage for the next 2 lessons that you're going to be learning. Tomorrow you'll be with Mr. Murphy, and he is going to talk about how to make and interpret a confidence interval for slope. And then I'll be back with you